Okay, we are going to think about now acceleration. Do you remember on Tuesday's lesson, we got to the point where we said a couple of different scenarios. We had one scenario where there was no resultant force. If there was no resultant force, can you tell me what was happening? Constant velocity or completely at rest, okay? And that was Newton's first law. I can never remember which one is which. Newton's first law, right? What was I saying? I've just gone completely mind blank. Yeah, so that was one of the things we were looking at, if there was no resultant force. Although when we were at this point here, when we were doing some force diagrams like this, do you remember we drew some resultant forces on? I think this one was like 2 to the left and 2 downwards, like this. And we started saying, well, what's that going to do? And we were like, it's going to make it accelerate. But we didn't say how much it was going to make it accelerate. We just knew this one was going to be accelerating in that direction. We had a sense of the direction, and we didn't know exactly how it would be accelerating. So we're just going to extend that now by introducing Newton's second law of motion. And this one I know that you do in GCSE because I saw some Year 11s revising for this. And the second law of motion is basically F equals ma. Now this F that we have here, this F, as I've written, is the resultant force. This is not just the force, but it is the resultant force. If you can just make that really, really, really clear to yourself, either by underlining this bit that we've got here, it is not just the force, it is the resultant force. And you remember how we did the resultant force? We did the forces in one direction, take away the forces in the opposing direction that we've got there. So this does feel right. I've said this kind of feels right as what the equation should be. I've said here, if we doubled the force, you would imagine that you would be doubling the rate at which it's accelerating. If you pull something twice as hard, you think it's probably going to accelerate twice as fast. Similarly, if we have an object of twice the mass, so if we make it twice as heavy, we would require twice the force to make it accelerate at the same rate. So this formula, F equals ma, is really connecting together how big something is, how much force is being acted upon that, and as a result, how that makes things accelerate, okay? Just by looking at F equals ma and knowing that F is the resultant force, what can you tell me if there is no resultant force? No. Tell me, what can you tell me just by looking at this? What can you tell me if there is no resultant force? There's no acceleration. We've already said that, didn't we? If there's no resultant force, there's no acceleration. Arisa said it means constant velocity. Someone else said it could be at rest. Okay? So it's just to show you the formula always works, whatever the situation is. Now I've got a diagram that we've got here, and I've got a 2 kilogram box that is on a surface, on a horizontal surface. And I've used this little arrow here. I'm just going to draw it again just so you can see how I would draw this. It's an arrow going to the right and a double arrow to show acceleration. If it was a single arrow, that would show a velocity. A double arrow shows acceleration. Why do you think it's got 2 arrows for acceleration? Because it's got like power of -2, you've got ms to the -2, whereas velocity's obviously just got ms to the 1. So if we wanted to work out some different things here, well, it's going to be accelerating to the right, which means that the resultant force is overall something is acting to the right here. It's not accelerating up or down though. Okay, so up and down, you should be able to tell me that up and down r is equal to 2g because there's no resultant force in that direction because it's balanced. It's not flying up into the air and not flying down into the table. So what I've written here is the resultant force we find by doing the forces to the right minus the forces to the left. That should remind you what we did earlier on. So we've got 45 minus 10 minus 5. That's what my F part is that I've got here. And it's equal to the mass, which is clearly 2 kilograms, times by the acceleration. Notice how I do this all as one single equation. I haven't gone force equals 45 minus 10 minus 5. I've done the entire thing all at once, and that's how I want you to do these. I want you to find out what's the resultant force and make it equal the mass times the acceleration, and then simplify as you go down. So when you go down, you get 30 equals 2a, so a equals 15. This tells me that the particle will accelerate at 15 meters per second squared to the right. Pretty straightforward about how that's happening. We're just combining what we did last lesson now with the fact that something is going to accelerate to the right. So I've got a few examples that I'm going to do here, and then you're going to do some practice. So this one here, I'll do this first one. You can try this second one in a second. It's accelerating at 2 meters per second to the right. And in each of these diagrams, we want to find the magnitudes of the unknown forces x and y. Can you immediately tell me what one of the sizes of these forces is, like straight away? Y is equal to 2g. Yeah, if we're resolving it in the up and down direction, we know it's not accelerating up and down, so I don't have to do any F equals ma. I can just say that they are equal to each other. So y is equal to 2g. And I'm happy to leave my answer in terms of g there, okay? But if I'm now going to be trying to resolve it in the other direction, if I'm going to try and find out the resultant force, I'm going to find the resultant force, and I'm going to take the right as my direction. Why am I going to take right as my direction? Because that's the direction it's accelerating in, okay? What's my resultant force to the right? Good, it is x minus 4. In fact, what I'm going to write here is I'm going to say I'm going to do this using F equals ma. So I get x minus 4 equals the mass, which is 2, times the acceleration, which is 2. So this is the resultant force, this is the mass, this is the acceleration. So I get x minus 4 equals 4, so x equals 8. Okay? Second question. Can anybody remember anything I've mentioned about how we draw force diagrams? Is there anything in this force diagram that you think I would probably draw in a slightly different way? Yeah, this 20m which is pushing into it, I would probably redraw this diagram, and I would like to do it like this. I would have y out the top, 20 out the bottom, 4g out the bottom. It doesn't actually matter, but I always prefer to have, where possible, the arrows coming out. Sometimes they will go in, but that's quite rare. And then to the right, I've got x, and to the left, I've got 80. You can see I've also avoided putting n on my diagram. I just don't like drawing newtons when I do my diagrams. And it's going to the left at 2. Okay, so this should make it a little bit easier to see now. If I resolve it up and down, what do we have? What is y equal to? Yeah, we've got the ones going up must be equal to these ones. And I can say they're equal because it's not accelerating in that direction. The overall resultant force is to the left and right, and I know that because of the acceleration. This time, I don't want to leave my answer in terms of g because I've got kind of like a mixture of things. So I'm actually just going to do 20 plus 4 times 9.8, which is 59.2 newtons. Which direction do you think I'm going to find the resultant force in for the second part to try and find out what x is? To the left or to the right? Left. Yeah, why am I going to do it to the left? Good, it's accelerating to the left, and that's where the direction of the resultant force must be. So if I'm going to resolve it to the left now to find the resultant force using F equals ma, I've clearly got this one is going to be bigger than this one because overall it's making it accelerate in that direction. So I get 80 minus x equals the mass, which is 4, times the acceleration, which is 2. So 80 minus x equals 8, which means that x is 72. Just want to show you something out of interest. And you don't need to write this down if you think you don't have to. Imagine I said, actually, I'm going to resolve it to the right instead, and I'll do F equals ma. Just imagining this question over here, but doing it to the right instead. What would the beginning bit be for the resultant force? It would be what, sorry? It would be x minus, it would be this one minus this one, which is x minus 80. The mass is still 4, but what could you say about the acceleration? Because it's minus 2, because it's in the other direction. So it would be multiplied by minus 2. So you get x minus 80 equals minus 8. So x equals 72. So you can do it either way, but it's always better to try and do it this way that I've done in black writing, because it matches the direction that the acceleration is going in. Okay, that's definitely the better way to try going about these questions. Okay, so a few worded examples. Little diagrams can be quite helpful here. A car of 2,000 kilograms has a driving force of 800 newtons and forces of 200 newtons resisting its motion. Determine its acceleration. So here's my car of 2,000 kilograms. It has a driving force of 800 and a resisting force of 200. So last lesson, I asked you to find the resultant force. This lesson, we go a stage further and we find out what the acceleration is. So it's obviously going to be accelerating to the right because this one is bigger than this one. So I'll find the resultant force to the right and then I'll use F equals ma. My resultant force is what? 600, yeah, it's 800 minus 200 and it equals the mass times by the acceleration. So we get 600 divided by 2,000 is the acceleration, which is 6 over 20 or 3 over 10 or 0.3. I'll just give you a second to write that down. What's that? Yeah, mechanics would probably go with a decimal for that. The difference that we'll do when we come back to this in year 13 is we won't have forces that are flat, we'll have forces that are maybe at an angle instead. So just so you know where this topic goes, everything we're always going to do is horizontal and vertical. Year 13, we have things that go at angles as well. Okay, so this one is really to try and investigate something that we probably already know the answer to, but it's to try and prove why it's true. Charmaine, looking this way, yeah? It says a child has a mass of 50 kilograms. What is the gravitational force acting on the child? What is its weight? So I'm going to draw a lovely picture of a child, which is here. And we've got some force, which is the force that you feel to gravity. We know that that's going to be the weight that you have, okay? So I'm going to call that the weight that's pulling down. And you can just imagine this child is just, we're trying to say, what is this weight equal to? Well, we know that F equals ma. And what is the acceleration downwards due to gravity? 9.8. And I'm just going to call it g because it could be a different gravitational force, but we're going to go with 9.8. So my resultant force overall in the downwards direction is w. The mass of the child is 50, and the acceleration is g. So do you remember earlier on in the last lesson I said the weight of the child, or the weight of whatever it is, was just mg, w equals mg. This is really a variation on F equals ma. That's why we say that the weight is w equals mg, because the weight is the force that is done by gravity. That's what your weight is there. So I've added this question in to try and explain why weight is why w equals mg. Okay, this time we have got a slightly different question. It says a falling sheep of mass 70 kilograms experiences air resistance of 300 newtons. Determine the sheep's acceleration as it plummets towards the ground. Now, will the sheep's acceleration be 9.8? Because normally things falling under gravity have acceleration of 9.8, don't they? Well, you'll see what will happen here. It's not to do with its mass, though. This is not going to have an acceleration downwards of 9.8. The only things that have an acceleration downwards of 9.8 are what we model as particles. What's one of the things that we do when we model something as a particle? What are we allowed to ignore? Air resistance. So if there's no air resistance, the acceleration will be 9.8. but this sheep is experiencing some air resistance, so it's not going to be accelerating quite as fast. It's a bit like if someone jumps out of a plane, they start off accelerating quite fast, but then they have a parachute, and the parachute changes their acceleration. Just because they're falling doesn't mean they're falling at 9.8. So again, I'm going to draw a lovely picture of a sheep, and I'm going to put in the weight of the sheep. The weight of the sheep is 70 what? No, 70 G. G is the weight. We're thinking at the moment of how humans in regular English say, what's your weight? When you say, what's your weight, you would say 65 kilograms. But when we say, what is your weight in mechanics, we're saying it's your mass times G. And the resistant force, because it's falling downwards, is 300. And we know that it is accelerating downwards because this sheep is doing a skydive, right? So again, we just do F equals ma, but this time we're going to be resolving downwards. We're going to find the resultant force downwards using F equals ma. So Taylor, what do you think the resultant force is for this one?
70 G minus 300.
Good, 70 G minus 300. The overall force going downwards is 70 G, but it's minus 300 because that's in the opposing direction. And that is equal to the sheep's mass, which is 70, times by A. So I'll do 70 times 9.8 minus 300, which is 386. And I will divide that by 70 to find out what the acceleration is. And when you divide that by 70, you get 5.51 meters per second squared to 3 significant figures. So it's quite a lot less than 9.8. That air resistance that sheep is experiencing, maybe it's got a little parachute on, is stopping it falling at the same rate that you would expect like a small stone to be falling at. A small stone won't have much air resistance. A big fluffy sheep with a parachute on is having enough air resistance to slow it down to a slower rate of acceleration that we have there. Okay? One more example, and then it's time for you to do some practice. So the only thing I wanted to show you on the next page is because these questions now include acceleration, we can use SUVAT. Okay? You might not remember this, but on the very, very first lesson of mechanics, I showed you like a big diagram, and on the right-hand side of the page, we had stuff to do with speed time graphs and integration and differentiation and SUVAT, and on the left-hand side, we had forces. And I said the one thing that bridges in between forces and SUVAT stuff was acceleration. So this is now why we're going to connect the topics together. And it says combining F equals ma with SUVAT equations. Since F equals ma involves both force and acceleration, it allows us to connect calculations involving forces with calculations involving SUVAT values. So let's have a look at what we've got here. And before we actually do that, the most important one to notice is F equals ma and SUVAT both have acceleration. So if you ever feel like you're stuck in one of these questions, you need to work out the acceleration because it's the bridging value that will take you between the two topics. A body of mass 5 kilograms is pulled along a rough horizontal table, meaning that it's got some friction, by a horizontal force of magnitude 20 newtons against a constant friction force of magnitude 4 newtons. Given that the body is initially at rest, find these 3 different things that we've got here. Now, everybody needs to draw diagrams for this. You may not need one in your head, but I know where this topic goes throughout the rest of year 12 and the rest of year 13, and I need you to be in the habit of always drawing a diagram. So I'm going to draw a rough horizontal table, and I'm going to draw a body of mass 5 kilograms. I'm going to start labeling more forces than I have done on the previous page. I'm going to include its weight, which is 5g. And what else could I include in the up and down direction? Is there any forces going up? What do we call this one up? The contact force. The contact force or the normal reaction, the reaction force. So we've got the R is going up there. We know that there is a force that's pulling it along of 20, and it says there's a constant frictional force of 4. Well, obviously a frictional force is trying to slow something down. It's going in the opposite direction. So we have 4 that is going to the right. Can anybody think of anything additional I can add to my diagram that might make it better? What was that, sorry? The direction of the acceleration. So Ibtiaz, which way is it going to accelerate? Towards the 20 direction. It's going to accelerate in this direction like this. Okay? Now, they haven't asked me to find this, but you could tell me what the value of the normal reaction is. Ibtiaz, what do you think is the value of the normal reaction? Wouldn't be 9.8. No, think about what we know about this, the up and down forces. What do we know about the up and down forces? They're the same. So R is just 5g in this case. They're the same as each other because it's not accelerating up and down. It's accelerating left and right. Red one, would you be able to do the resolving for me and tell me which direction you want to resolve it in? So you're going to resolve it to the right using F equals ma. So it becomes 20 minus 4 is the resultant force. And what's that equal to? Yep. That's the thing we don't know. We don't know what that is. Acceleration isn't g here. The only time the acceleration is g is when you're dropping something on the floor, okay? This is not dropping on the floor, so its acceleration is not going to be g. Just because we did Suvat that had g for the acceleration does not mean that everything has an acceleration of g. So 20 minus 4 is 16. 16 divided by 5 is the acceleration, which is 3.2. Part A of the question is done. Now you can see how you could connect this with some Suvat questions. I'll give you a second just to write that down. No, because mass is 5 kilograms, weight is 5g. Okay, so weight is the force, mass is just how much stuff there is. So it's not F equals WA, it's F equals MA. Good question though, because you need to make sure you've understood that these bits are different. So for part B, we want to find the distance travelled by the body in the first 4 seconds. So clearly they've told me that the time is 4. What else do I know? The acceleration is 3.2. U is 0 because it starts from rest. And I'm trying to find S. What connects those? S equals ut plus a half at squared. So S is equal to 0 times 4 plus a half times 3.2 times 4 squared, which is 26.6 or something. 25.6. 25.6 meters. Suvat. Same as before, right? The magnitude of the normal reaction between the body and the table. I didn't even realize that was part C of the question. We've already done that, haven't we? I asked Ibtiaz about that at the beginning. The normal reaction, when we resolve in the up and down direction, there's no resultant force there because it's not moving up or down. It's at rest in that direction. So we just get R equals 5g. If you want to put that as a number, why not? You don't have to. So R is 49 newtons, okay? I'd like you to have a go at the question that is on the next page, I think. Or did I want to do this one? No, we don't want to do this question yet. We're going to have a look at this question later on. We're going to try exercise 10C, and I'll tell you which questions that we want to do. And we'll do these on the whiteboards because I want to see your diagrams.